What do these three images have in common? Well, they're all examples of what we call solutions. First off, the definition of a solution. A solution is a homogeneous mixture containing two or more pure substances. The major part we call the solvent, and the minor parts, or part, the solute. Let's look at a few examples. For instance, the solution that we call seawater. Of course, the major ingredient would be water, but the solutes would be several salts. They might include sodium chloride, magnesium sulfate, potassium chloride, and on we go. Club soda. Again, the major ingredient would be water. And the solute, what gives us its fizz, carbon dioxide gas dissolved in that water. Wine is an example of a solution, the major ingredient being water, and one of the minor ingredients being ethanol. There would also be several tannins present as well that give it its particular color or flavor. You'll notice that all of these solutions so far have had water. Water is what we consider to be the universal solvent. It's capable of dissolving many substances, in particular polar substances and ionic salts. Air is an example of a solution, but this one is a gaseous solution, the major ingredient in air being nitrogen gas, making up some 80% of air. Oxygen about 19%, and then several trace gases, carbon dioxide, water vapor being amongst them. And finally, an example of a solid solution, brass, the major ingredient in brass being copper, and the solute in brass being the metal zinc. Brass is what we call an alloy, so alloys are examples of solutions. This particular unit is going to deal particularly with what we call aqueous solutions, solutions involving water. And the concentration of a solution is often expressed as some amount per liter or per decimeter cubed. Now, the amount of solute could be expressed in a variety of ways, but the most common way to express solute, at least in chemistry, is with moles, the moles per liter. And we often call this the molar concentration. And it can be calculated by putting the number of moles divided by the volume expressed in liters or decimeters cubed. Several household chemicals might resort to the use of expressing the amount of solute in grams, and hence the concentration would be the mass over the volume, giving you units of grams per liter or grams per decimeter cubed. In very dilute solutions which have very little solute, we often use the expression of parts per million. And parts per million, we express the amount of solute in milligrams and the volume of the solution in liters or decimeters cubed. So very similar to the concentration using mass over volume, but we make sure we express the mass in milligrams. Let's take a look at some of these units to express one particular concentration. So here is the composition of seawater. I'm going to focus in particular on the concentration of the potassium ion that's present. So from this graphic, I can see that the potassium ion, there's 0.39 grams present in 1 liter of seawater, or 1 decimeter cubed. I'm going to express this particular concentration in moles per liter, or moles per decimeter cubed. The given information I have is 0.39 grams of the potassium ion. The volume of my solution is 1 decimeter cubed, or 1 liter. But also implicit in this is the molar mass of the substance. Because I'm talking about potassium, the molar mass of the potassium ion is 0.39 grams per mole. Now, with that particular bit of knowledge, that'll be similar to what the potassium ion is. The loss of 1 electron won't change the molar mass much. From that, I can calculate the number of moles by taking the mass and dividing by the molar mass. I'm keeping one more significant digit than I need here at this point. Once I have knowledge of the number of moles, I can calculate the concentration by putting the number of moles over the volume. Now you'll notice here that I've rounded my answer off to 2 significant digits, because when I go back to my given information, the 0.39 grams, that has but 2 significant digits. A B part of this question is going to ask me to express this concentration in parts per million. So again, I go back to my given information. To express it in parts per million, I must change the grams to milligrams by shifting the decimal 3 to the right and turn the 0.39 into 390 milligrams. To calculate the parts per million, I put the mass over the volume and I get 390. If I want to express this in scientific notation so there's no ambiguity about significant digits, it would be 3.9 times 10 to the 2 parts per million. Let's look at a second example. The student prepares 250 milliliters of a 0.0200 mole per liter zinc chloride solution. My first question is I want to determine the moles of chloride that are present in the solution. Again, my given information, I have the number of moles and the volume and the concentration. You'll notice here that I've employed the use of square brackets. By convention, it's quite often that the use of square brackets is used to designate the concentration in moles per liter. Now, before I go and substitute and solve here, I'm just going to make note of the units. I have moles per liter and milliliters. I want to convert those to be in the same units, so I'm going to change that milliliters into liters. Now the equation, and now I'm going to rearrange it to get the number of moles by itself on one side. So concentration times volume. You can see here the liters would cancel out, leaving me 0.00500 moles of zinc chloride. Now, when zinc chloride dissolves, it forms two chloride ions. Here I've shown the equation for it. So at this point in time, I have 0.005 moles of zinc, but my question's asking me about the chloride ion. The ratio from the equation indicates 1 to 2, so I need to double that number of moles. Hence, the number of moles of my zinc ion is 0.0100. Now, a little bit about significant digits. If I look back at my original information, there's 3, and my final answer should have 3. The B part of this question would like to know what mass of zinc chloride I used to make this solution. So from my answer up above, I'm using the number of moles and the molar mass then of zinc chloride. The number of moles is the mass over the molar mass, and hence rearranged to get the mass by itself. I just need to multiply the moles by the molar mass. The moles will cancel, leaving me in grams. Hence 0.681 grams of zinc chloride. Thanks for watching, and please post any questions.